In this module, you will study the inverse of a bijective function. Right from your school days, you learned to find the inverse of real numbers. For example, the additive inverse of 2 is -2. The additive inverse of 1 by 2 is -1 by 2. The additive inverse of -1 is 1, and the additive inverse of -1 by 9 is 1 by 9. It is to be noted that, on adding the inverse of a number to it, we get 0, which is the identity of the set of real numbers over addition. Now, let's see if the inverse of functions exists. Let us denote the set of numbers 2, 1 by 2, -1, and -1 by 9 by A, and the set containing the additive inverse of the elements of set A by B. Define a mapping F from A to B such that F maps the elements of set A to their additive inverses in set B. Observe that F is 1, 1 and onto. Now, let's define a function g from B to A such that it maps the numbers in set B to their additive inverses. That is, g maps the elements of set B back to set A. Such a function g is known as the inverse of f. This discussion leads us to the definition of inverse function. Let f be a function from A to B if for any arbitrary element x belonging to A, we have f of x is equal to y in B. Then the function g from B to A given by g of y is equal to x, where y belongs to B and x belongs to A, is called the inverse function of f. Let's now move on and see when a function is said to be invertible. Let 2 be an arbitrary element in set A. Then g circle f of 2 is equal to 2. In general, g circle f of x is equal to x for all x belonging to set A. This implies g circle f is an identity mapping on A. Let's now see if f circle g is also an identity mapping. Consider any arbitrary element, say -2, in set B. Then f circle g of -2 is equal to -2. Generally, f circle g of x is equal to x for all x belonging to set B. This implies f circle g is also an identity mapping on B. Here the composition of f and g and f is an identity mapping. Such a function f is said to be invertible. Mathematically, a function f from A to B is said to be invertible if there exists a function g from B to A such that g circle f is an identity mapping on A and f circle g is an identity mapping on B. The function g is called the inverse of f and is denoted by f with superscript -1. Let's proceed further and learn to find the inverse of a function with the help of an example. Let P be the set of all y such that y is a natural number and is equal to 3x minus 2. Let's show that a function f from n to p, defined by 3x minus 2, is invertible, and let's also find its inverse. Let's begin by considering an arbitrary element, y, in set P. This implies y is equal to 3x minus 2 by the definition of set P. This further implies that x is equal to y plus 2 whole divided by 3. Let us now define a function g from P to n by g of y is equal to y plus 2 whole divided by 3. Now, g will be the inverse of f if g circle f and f circle g are identity mappings. Let's check it out. Consider any arbitrary element, x, from the set of natural numbers. Then, g circle f of x is equal to g of f of x, which is further equal to g of 3x minus 2. And, by the definition of function g, this is equal to x. This shows g circle f is an identity mapping from n to p. Next, let us consider any arbitrary element, y, from set P. Then, f circle g of y is equal to f of g of y, which is further equal to f of y plus 2 whole divided by 3. And by the definition of function f, this is equal to y. This shows f circle g is an identity mapping from P to P. So, from equations 1 and 2, we can say that f is invertible and g is the inverse of f. Now, let's prove one theorem. Let f and g be two invertible functions from x to y and y to z respectively. Then, the composition of f and g is also invertible. That is, the inverse of the composition of f and g is equal to the composition of the inverse of g and the inverse of f. Let's begin with the proof. We are given that f and g are invertible functions. We have to prove that g circle f is invertible, with g circle f inverse equal to f inverse circle g inverse. To prove g circle f invertible, it is sufficient to prove that the composition of g circle f and f inverse circle g inverse is an identity mapping from x to x, and that the composition of f inverse circle g inverse and g circle f is an identity mapping from z to z. Let's begin with the first part. By using the associative law of composition of functions, the composition of g circle f and f inverse circle g inverse can be written as the composition of f and f inverse circle g inverse circle g. Again, using the associative law, the terms inside the curly brackets can be written as the composition of g inverse circle g and f inverse. Now the composition of g and g inverse is an identity mapping from y to y. Also, the composition of identity mapping with f inverse is f inverse. So we get f inverse circle f, which is again an identity mapping from x to x. Hence the composition of g circle f and f inverse circle g inverse is an identity mapping from x to x. Similarly, we can prove that the composition of F inverse circle G inverse and G circle F is an identity mapping from Z to Z. From equations 1 and 2, we conclude that the inverse of the composition of F and G is equal to the composition of the inverse of G and F. Hence, we can say that the composition of two invertible functions is also invertible.